Imagine you are seated beside a window, gazing out at the night sky adorned with countless stars, and pondering the profound mysteries of the universe. Have you ever wondered why, when an object attains the speed of light, time would cease to flow? If you have encountered the concept of time dilation, you are undoubtedly aware that the closer one approaches the speed of light, the more slowly time passes. Yet, have you ever contemplated what would transpire to time if we were to accelerate precisely to the speed of light? According to Einstein's theory of relativity, at the very instant you genuinely reach the speed of light, your time would come to a complete standstill. To grasp this revolutionary conclusion, we must first examine just how extraordinary the speed of light truly is. From our secondary school physics lessons, teachers informed us that the speed of light represents the absolute limit of the universe, akin to an invisible barrier that cannot be surmounted. Most of us dutifully accepted this decree, but few truly questioned the underlying logic. Is there genuinely some unseen hand restraining us within space? The reality proves far more astonishing than any cinematic depiction. Einstein revealed to us that upon truly attaining the speed of light, the entire framework of the universe would collapse. You would no longer be bound by time. This may sound like an outlandish theory. However, to prevent your escape, the universe has indeed engineered an impeccably airtight chain of logic. To unravel this enigma, we cannot merely scrutinize Einstein's equations. We must journey back to the 17th century. Let us explore how humanity first uncovered the secrets of the speed of light. The tale commences at the Paris Observatory in the year 1676. At that juncture, the majority of people believed that light propagated instantaneously. When a star was born, its light immediately suffused the entire universe. However, there was a Danish astronomer named Ole Romer. He was a profoundly earnest individual, with eyes perpetually directed towards the dark, chilly night sky, where stars twinkled like distant candles. He devoted numerous nights to observing one of Jupiter's moons, Io. Envision him seated there, in a dimly lit chamber illuminated solely by the flickering glow of candles, meticulously recording each movement of Io through a rudimentary telescope. He discerned a peculiar phenomenon. When Earth moved to a position farther from Jupiter, the eclipses of Io appeared invariably delayed, whereas when Earth was nearer to Jupiter, the eclipses arrived prematurely. In that era, this was dismissed as mere observational error, perhaps attributable to the cold night winds fogging the lens or fatigue from sleepless vigils. Yet Ole Romer possessed an extraordinarily audacious intuition. Could it be that light requires time to traverse space? This marked the inaugural occasion when humanity realized that light is not a phantom. It, too, is a hasty messenger. When Earth is distant, this messenger of light must travel an additional distance. Consequently, the news arrives belatedly. Although the data he calculated at the time was not entirely precise, he estimated the speed of light at approximately 220,000 kilometers per second, somewhat lower than the actual value of 300,000 kilometers per second. He nonetheless unlocked the gateway to modern physics. Light possesses a speed. And this was not merely a fortuitous discovery. It ignited a cascade of new inquiries, compelling subsequent scientists to reflect more profoundly on the universe's operations. Today, we understand that Romer's finding hinged upon observing the eclipse cycle of Io, and it has been refined through contemporary measurements, such as employing radar to gauge distances to planets, affirming the speed of light precisely as 299,792 kilometers per second in a vacuum. Recent advancements, including laser ranging to the moon and precise timing of signals from spacecraft like the Parker Solar Probe, have further corroborated this value with unprecedented accuracy, ensuring its foundational role in fields ranging from telecommunications to astrophysics. If light has a speed, then relative to whom does it move? This question precipitated one of the greatest upheavals in 19th-century physics. Scientists of that period posited that if light is a wave, it necessitates a medium for propagation, much as water waves require water, and sound waves require air. They bestowed upon this hypothetical substance a poetic name, the ether. Initially, people conceived of Earth gliding through an ocean of ether, akin to a boat drifting on a river. When traveling downstream, the speed of light would accelerate, whereas upstream, it would decelerate. Picture the scientists of that age, in laboratories laden with dust, redolent of aged wood and metal, engaging in fervent debates about this ether, as though it were an invisible ocean enveloping everything, bearing mystical winds. To detect the ether, in the year 1887, two eminent scientists, Albert Michelson and Edward Morley, conducted an experiment of extraordinary precision. They utilized an apparatus known as an interferometer, an intricate system of mirrors mounted on a substantial platform that could rotate freely atop a pool of mercury to eliminate vibrations, resembling a vessel gliding smoothly over tranquil waters. This experiment transpired at Case Western Reserve University in Cleveland, Ohio, within a shadowy basement where the ticking of clocks mingled with the whispers of the scientists. They projected beams of light, ordinary light in those days, along two perpendicular paths, one parallel to Earth's presumed motion through the ether, and the other perpendicular. If the ether existed, they anticipated observing a shift in the interference fringes, akin to ripples on a lake stirred by the wind. Yet the outcome sent a chill through the entire physics community. There was no alteration whatsoever, irrespective of the direction of light propagation. Whether you pursued light or fled from it, the measured speed of light remained utterly identical, unchanging. This flagrantly contravened the notions of absolute space and time that Isaac Newton had established for centuries. Just as bewilderment gripped everyone, evoking a sense that the edifice of physics teetered on collapse, with heated debates at scientific conferences where applause intermingled with sighs of dismay, Einstein, then merely 26 years old, stepped forward. He regarded the invariant speed of light, and proposed a seismic idea. If the speed of light remains constant regardless of measurement method, then something else must yield. To safeguard the unchanging speed of light as a cosmic boundary, we must sacrifice two pillars we deemed most unassailable: time and space. This was the birth of the special theory of relativity, in the year 1905, when Einstein published his theory in a modest paper that nonetheless shook the world. Einstein informed us that when you endeavor to chase a beam of light, the universe ensures you perceive its speed steadfast, at 300,000 kilometers per second. To achieve this, it must distort your time. It is not that your clock malfunctions, rather, time itself elongates. The swifter your velocity, the more the universe, in preserving the constancy of light's speed, retards the passage of your time. This is no mere mathematical sleight of hand, but a mad compromise the universe enacts. Envision yourself aboard a spacecraft hurtling through the inky void, with the hum of engines and the surge of adrenaline as velocity mounts, and suddenly you realize your clock lags behind those at home, as if time stretches each second to maintain cosmic equilibrium. This theory is not abstract conjecture. It has been validated through innumerable modern experiments. For instance, in the Haefel-Keating experiment of 1971, scientists transported ultra-precise atomic clocks aboard aeroplanes circumnavigating the globe eastward and westward, comparing them to ground-based clocks. The results demonstrated that the airborne clocks lagged precisely as Einstein predicted, incorporating both velocity-induced time dilation and gravitational effects from general relativity. Or consider muons, fundamental particles generated by cosmic rays colliding with Earth's atmosphere. Muons possess a brief lifespan, merely 2 microseconds at rest, yet owing to their near-light speed travel, their time dilates, enabling them to traverse greater distances and reach the surface, something impossible without time dilation, as they would decay forthwith. At particle accelerators, like the ESR, at the GSI Helmholtz Center in Germany, scientists have measured time dilation at velocities of 34% of light speed, confirming Einstein's formula with exquisite precision. Even in the Ives Stilwell experiment, they gauged the frequency shift of light from fast-moving ions, proving time slows exactly as theorized. More recently, observations of distant supernovae have provided the clearest evidence yet for cosmological time dilation, where the apparent slowdown of exploding stars' light curves aligns with relativity's predictions, extending our confirmation to vast cosmic scales as of studies published in 2024 and refined in 2025. Additionally, experiments with optical clocks at institutions like the National Institute of Standards and Technology have verified gravitational time dilation at minuscule height differences, underscoring relativity's pervasive influence. Now, let us return to the initial query. What would occur if I truly attained the speed of light? We might conceptualize space-time as a finite budget. The more rapidly you traverse space, the less allocation remains for time. As you accelerate wildly, nearing the speed of light, your temporal rate compresses ever slower. Centuries might elapse as a mere instant for you. And upon precisely reaching the speed of light, your spatial velocity consumes the entire budget. At that point, the allotment for time becomes nil. This signifies that for a photon, it departs the sun's surface, journeys across 150 million kilometers, and ultimately collides with your retina. In our perception, this consumes 8 minutes and 20 seconds, but for the photon, the entire voyage expends no time whatsoever. Departure and arrival coincide. In its realm, there is no past nor future, solely an eternal present. The notion of time there utterly disintegrates. Contemplate the photon as an immortal envoy, surging through the cosmos without sensing time's weariness, bereft of memories from the interminable journey, simply existing from origin to terminus in an everlasting moment. From the photon's vantage, the universe contracts to zero thickness, and time vanishes, resembling a serene painting where all events unfold simultaneously. This inference stems from the time dilation formula, where the Lorentz factor approaches infinity at light speed, rendering the photon's proper time zero. Social discussions on platforms like X have echoed this, with users illustrating how constant light speed across distances necessitates time dilation, reinforcing the concept's intuitive grasp. That is why we can never achieve the speed of light. For mass holds the ultimate key. As you approach the speed of light, your mass becomes infinite. Infinite energy would be requisite to propel it. In truth, we refer here to relativistic mass, not the invariant rest mass. As an object accelerates, its kinetic energy escalates, and per the equation E equals mc squared, this energy equates to augmented effective mass, rendering further acceleration increasingly arduous, akin to shoving an ever-enlarging snowball up a steep incline. The universe seems to proclaim in this extreme manner that matter pertains to time, whereas light belongs to eternity. We are ensnared on the sluggish lane below light speed. Yet perhaps this is not a misfortune. Precisely because we cannot attain light speed, time courses through us. We can thereby experience growth, aging, memories, and aspirations. The speed of light is the universe's key. But it is also the protective umbrella it bestows upon us for existence, anchoring us within time's flow so we might lead a full life. And in the year 2025, this theory transcends abstraction. It finds practical embodiment in technology. For example, the Global Positioning System must compensate for time dilation. Clocks on satellites run slower due to their high velocities, and faster owing to diminished gravity, necessitating a net adjustment of about 38 microseconds daily for your location's accuracy. Absent relativity corrections, GPS would drift by kilometers each day. Furthermore, scientists are harnessing relativity's principles to forge quantum computers, where manipulations of time and space could expedite information processing, ushering in a new era for medicine and artificial intelligence, such as simulating drug interactions or modeling cosmic phenomena with unparalleled fidelity. Approaches inspired by light cones from special relativity are even aiding artificial intelligence in forecasting future events, potentially revolutionizing predictive modeling in healthcare and beyond. These developments evoke exhilaration, as if we are touching the universe's deepest secrets, and remind us that knowledge from yesteryear continues to sculpt our future in marvelous ways.